Good afternoon, everyone. So now I would like to invite Mr. Kaushal Ageta, a passionate teacher, assistant professor at the Department of Applied Physics, Faculty of Engineering and Technology, the Maharaja Sayajirao University of Baroda, Gujarat. He is also an active member, the chairperson of Gujarat chapter of AIP. I welcome you, sir.
Welcome, Kaushal sir.
Can we start, sir?
Yeah, sir, sure.
Okay, okay. Let me present my screen. Okay, sir. Can you see my screen properly?
Yes, sir, it is really well.
Okay, okay. So good afternoon, everyone. My name is Kaushal Ageda. I am assistant professor in applied physics department. I am at University Baroda, Gujarat. I am also a chairperson in AIP, Association of Indian Physicists. Today we are discussing advanced spectroscopy, applying a density functional theory with ORCA software. Let us start. So today's outline of my session are kindly spectroscopy. What is spectroscopy and all this? Or which type of spectroscopy are we studied in our research and PG level and UG level? Then we briefly introduce or briefly discuss about ultraviolet visible spectroscopy. Then after APR spectroscopy, NMR, and what is ORCA software, or a brief about ORCA software. And then after we will move on to the hands-on session. So spectroscopy. So basically a study of interaction between a matter and electromagnetic radiation. It is called a spectroscopy. So what is the fundamental aspect of the all this kind of spectroscopy? So interaction with electromagnetic radiation, which means that the spectroscopy measure how different wavelength of light are absorbed, emit, and scattered by materials. Spectrum, the result of the spectroscopy analysis showing the intensity of light as a function of wavelength or frequency. Quantitative and qualitative analysis. Spectroscopy can be used to identify substances, qualitative, and to measure the amount of substance in the sample. It is a quantitative. So there are so many types of the spectroscopy. So first one is absorption spectroscopy. So in absorption spectroscopy, the measure amount of light absorbed by sample at a different wavelength and catch after through the sensor, and we are getting some information about the sample. So for the particular for the absorption spectroscopy, there are two kind of spectroscopy are there: ultraviolet visible or UV visible spectroscopy and infrared spectroscopy. In both spectroscopy, we can easily see that our radiation coming from the sample. Okay, so some amount of the energy or radiation kindly absorbed by the particular sample, and we are getting, or we can easily trace uh, in this sensor. So UV visible spectroscopy used to analyze absorption of UV and visible light by sample, and that is some kind of give a more information about or different information about these two in spectroscopy. So in UV visible spectroscopy, we can easily identify that the structure through absorption spectra or peak of the absorption spectra. Uh, and in infrared spectroscopy, we can easily find out the vibrational frequency between two atomic bond or two atom. So it is a very important thing for these two spectroscopy. Then after emission spectroscopy. So in emission spectroscopy, the study the light emitted by sample when it's excited by external energy source. So in that particular emission spectroscopy, it's kindly flame emission spectroscopy, atomic emission spectroscopy, fluorescence spectroscopy, Raman spectroscopy, nuclear magnetic resonance, NMR spectroscopy, and mass spectroscopy and X-ray spectroscopy. So there are kind of spectroscopy which fall under the emission spectroscopy kind of thing. Yeah. So you can see that again some kind of table, type of spectroscopy, usual wavelength range, usual wave number or range, and type of quantum transition. So again, we already told you that uh, all the spectroscopy covered or give a different information of the sample. Okay, through this quantum transition. So in first one, gamma emission, it's a nuclear transition, or X-ray absorption emissions, fluorescence and diffraction. It's an inner electron transition. So this transition of the electron and any kind of thing, we get different information from this. So basically, we are just putting out electron spin resonance and nuclear magnetic resonance, and we will study or we will discuss later for these three kind of spectroscopy: UV, EPR or ESR, and NMR. Okay. So basically, for in the UV visible spectroscopy, the spectroscopic process in UV spectroscopy, the sample is irradiated with a broad spectrum of the UV radiation. If a particular electronic transition matches the energy of a certain band of UV, it will be absorbed. Will be absorbed. So if suppose we have a sample and it's a kind of a transition energy, okay, it's the same as a given UV visible, then it's but naturally it's absorbed, and we get some kind of absorption peak over there, and we can easily find out which kind of material or which material is there in this sample. Okay, so the remaining UV light passes through the sample and it's observed. From this residual radiation, a spectrum is obtained with gaps at this discrete energy. It is called absorption spectra. You can see that here it's kind of a gap is shown in this figure. So it is called again. It is called absorption spectra, and absorption spectra is kind of, you can see that the peak kind of thing, okay, at particular wavelength, then we can easily find out which material is there. Okay, observe electronic transition. Here is a graphical representation. You can see that here, and it's a excited state, pi star, sigma star. Here a pi and sigma, it's molecular orbit, okay, atomic orbit, occupied level or unoccupied level. For what? For the electron. Okay, so electron occupied level and unoccupied electron level. So electron is a transition through this lower part to the higher part. Okay, so in detail of this molecular orbit diagram, there are several possible electronic transition that can occur, each of different relative energy. Okay, you can see that if a transition between sigma to sigma star, it's alkane, sigma to pi star is a carbonyl group, pi to pi star is unsaturated compound, and to sigma star is ONS or halogen kind of thing, and n to pi star is again carbonyl. Okay, so this kind of transition, we can easily find out this group of the function. Okay, so again, here we are using absorption and Beer-Lambert's law. So its law is very simple. Okay, so there are two things. Light is diminished as it passes through the atmosphere, and mathematician is called as a first to prove that pi is irrational, no absorption coefficient. Okay, so this equation for the absorption spectra, or we can easily find out here kind of E, okay, or epsilon is a extinction coefficient, C is a concentration, and L is a path length. If we are increasing this path length, then again absorption is increased, and if concentration is also if increasing, okay, then also we can easily know that we can assure that our absorption is high. Okay, when we are controlling a concentration or higher concentration, and we are increasing our path length, okay, then but obviously our absorption is higher, and that is basically it's a Beer-Lambert's law, which we have used in this UV spectroscopy. So, from the experimental point of view, three other consideration must be made. I already discussed. A longer path length L through the sample will cause more UV light to be absorbed, or linear effect. The greater the concentration C of the sample, more UV light will be absorbed, linear effect. And some electronic transition are more effective at absorb of photon than other. Its molar absorptivity sigma. This may vary by order of magnitude. So let us go through the EPR spectroscopy. So what is the EPR? So E for the electron, P for the paramagnetic, and R for the resonance. Or sometimes people call ESR spectroscopy. So both are same. EPR is equal to ESR. So electron. But here it's a very important thing is that we are only studied the unpaired electron spin and their interaction with their environment. Okay, so we cannot study the pair electron, okay, in this spectroscopy. So it is very important thing. If we will we will do later experimental or hands-on training, so in that particular we just choose kind of that material or molecule which have a kind of unpaired electron. Okay, then and then we can do this hands-on or DFT on it. Then spin, electron spin is a quantum mechanical phenomena. It is represented by ms, one of the four quantum number, n, l, m, ms. Ms can have only two value, plus half and minus half. In the language of quantum mechanics, this fundamental property of an isolated electron is an angular momentum. It can be described in classical physics model as if it were a spinning electric charge. So it is called electron spin. However, one second. So, however, this is just a mnemonic model and does not mean that electron is really spinning charge. So, it is very important thing. If you learn quantum mechanics, then you easily understand what it mean. Okay, so it is not actually spin, but you can say that yes, it's a mnemonic model. Okay, so electronic spinning in own axis. Okay. Paramagnetic. So, what is the paramagnetic? So, the general term paramagnetic used to describe material that are attract to magnetic field. There are two major contribution to paramagnetism: spin and orbital angular momentum. Since the term paramagnetic is more general and no free radical has only spin angular momentum without orbital angular momentum, EPR is a more precise term than ESR. Okay, and resonance. So resonance is means that whenever inner frequency match the external frequency, that it's term or some kind of matching these two frequency, that is called resonance. Okay, or in this spectroscopy, or in this EPR spectroscopy, some uh, frequency, some external frequency matches with kind of rotation or spinning electron. Okay, the frequency of the spinning electron, then and then resonance is produced. Okay, so and there is a most important term in EPR, which is resonance. The concept of resonance is central to the power of magnetic resonance technique. So type of paramagnetic substance, the stable paramagnetic, you can see that NOO2 or NO2. And unstable paramagnetic substance is radical ions and free radicals. So radical means again it is unpaired electron. It's having a unpaired electron. So let us understand the Zeeman energy level splitting. You can see that here the electron spin angular momentum quantum number ms. It's a plus or minus half. Okay, and you can see here, so degenerate state, and in this state we are not applying any magnetic field. If we are applying a magnetic field, then you can see that it's alpha state and beta state. Alpha state having a plus half ms, or electron spin angular momentum, and here is a minus half for the beta state, and in the presence of magnetic field, and it is called a Zeeman effect. If so again we are applying a strong magnetic field, there is a kind of you can see that you already know that a hyper splitting kind of thing it's happen. And you can see that equation delta E is equal to h nu is equal to small g capital B and h. Let us see what is it. So the equation describes the absorption of microwave energy between two spin states. So here a delta E, not a small d or d kind of, it's a delta E is equal to h nu. We already know this equation. When absorption and transition is there, okay. So the energy is emitted through or kind of energy difference between these two states is a delta E, and it is a G, beta, and H. H is applied magnetic field, beta is Bohr magneton, and G is a very interesting thing. Okay, so it's a characteristic of a radical and is 2. Proportionality constant factor, or you can say the splitting factor or Landau splitting factor. You can easily tell what about G. And in our experimental or in hands-on training, we are finding out G as well as hyperfine splitting constant. Okay, it's A and it is in form of a tensor. Okay, and also G is also in form of tensor. We will see later in the hands-on portion. So ESR spectra of a single electron. For the single electron, you can see that here H is equal to 0 and here is H is equal to not 0. And we are getting a singlet thing. Okay, we are getting kind of this spectra for the singlet. Then after, okay, so this is for the triplet state. Okay, triplet state. And you can easily see that here again, it's a hyper HFS. It means a hyperfine splitting is there, is not equal to 0. It means that again, beta state having splitting in 3 state. ML is equal to -1, ML is equal to 0, ML is equal to +1, and transition between these two upper and lower hyper splitting kind of state, we can easily find out, or we can easily get kind of spectra over there. Okay, so it is about the EPR spectroscopy. Okay, uh, let us move on the NMR spectroscopy. So spinning proton create a magnetic field. We already know that. With no external magnetic field, the nuclear magnet are randomly. So here world apply nuclear magnet. Okay, so randomly oriented. If or in the magnetic field, the nuclear magnet are oriented with or against d0 or against with direction of the magnetic field or against the direction of the magnetic field. So if we again put it over here for the in the magnetic field, you can see that alpha state and beta state. We already discussed about alpha and beta state. Yes, yes, you can see that here, alpha and beta state. If we are applying a magnetic field, if we are applying magnetic field, so irradiation with absorption of h nu or energy. So you can see that both beta beta kind of or alpha alpha kind of thing. Okay, if direction is different or in opposite, then here alpha alpha or up kind of state over here. You can see that again it's a diagram alpha beta. Okay, both are in different direction, against field and with field. If we are getting or if we put energy over there or radiation over there, then the absorption of the absorption take place, and this electron is goes to the excited state. Okay, and beta beta kind of. So in NMR we are getting a shielding and chemical shift. Okay, so what is the shielding and what is the chemical shift? Let's see. So proton in given environment absorb in predictable region in NMR spectrum. Two important factor: electronegativity, magnetic anisotropy. So here electronegativity also we can find out from the HOMO-LUMO analysis. So we are not showing over here in hands-on HOMO-LUMO analysis, but uh, we just I will idea, or I will give some idea about that HOMO-LUMO analysis in the hands-on. Okay. So in isolated proton nucleus over here, and the nucleus field B0 only, but the proton surrounded by electron density, the magnetic field introduced by the electron opposed to B0, the induced field decrease the strength of the magnetic field felt by nucleus. This nucleus is shielded. Okay, so shielding means that the covering of electron density of the nucleus. Okay, that is called a shielding. So there is a shielding effect and de-shielding effect. So in the shielding effect, an electron shield the nucleus, and absorb the shift of field. So whatever we are getting kind of absorption peak for the proton, it is up field. Okay, so proton plus electron. So that is called up, means that it's a move towards the left side. Okay, that is called up field, and down field is basically its peak is move about to the right side. Okay, so it is called a de-shielding effect. A decrease electron density, de-shield nucleus. The absorption shift is a downfield. Okay, so the degree of the shielding of nucleus depend upon its surrounding electron density. Adding an electron increase the shielding, or remove electron cause de-shielding. So this thing is happened. So again, hydrogen NMR spectra, and NMR spectra is a plot of intensity of peak against its chemical shift measured in parts per million. Parts per million. Here we are getting some, or we are having some molecule. Okay, and you can see that the chemical shifting. Okay, so downfield direction in upfield direction, and from this shifting of the in measuring in ppm. Okay, ppm, we can easily find out which hydrogen. Okay, or hydrogen having a shielding or not. Okay, so we can find out that the structure of the molecules where hydrogen is there, and uh, which kind of atom is with hydrogen on. Okay, so again we will discuss, or we can easily see from this session, hands-on session. We will totally describe or brief of the NMR spectra, or what is the hydrogen NMR spectra and what is the carbon NMR spectra. We will see the later. The structure information from the feature of one hydrogen NMR spectrum. So position of signals indicate the what type of hydrogen the molecules contain. Number of signal indicate the number of different type of hydrogen in molecules. Intensity of signal, they indicate the relative amount or how many of each kind of hydrogen in molecules. And spins splitting of the signal give a further uh, information of the neighboring environment for the various hydrogen in molecules. So this all three we are discussing three kind of spectroscopy: UV visible spectroscopy, again then after EPR spectroscopy and NMR spectroscopy. So let us understand ORCA software. So it is a very newly or it's a very easy to learn or easy to do the calculation of the DFT and more over molecular dynamics also you can do it in this software. So ORCA is a versatile and powerful computational chemistry software package designed for quantum chemistry calculation. It is particularly useful for density functional theory and ab initio methods. Here are some key points about ORCA. You can see that DFT and beyond, while ORCA excel in DFT calculation and support a variety of other methods, including a Hartree fog, MP2, uh, uh, then couple cluster and semi-empirical method. User friendly, it is a very user friendly. It's not kind of coding and all this. Just click a button and paste some kind of a syntax of the ORCA software, and you can get your answer. Okay, you can get your result of the any material, any sample, liquid form, gas form, even the liquid crystal, solid crystal, amorphous, any kind of calculation you can uh, do with this help of this software. uh, Okay, so efficiency ORCA is designed to be efficient on modern computational architecture. It supports parallel computing, which can significantly speed up the calculation. So feature, so geometrical optimization, frequency calculation, electronic spectra, solvent effect, NMR and EPR spectra. So this thing is covered in this session or in after this session. So I think one participant asked in first session if we do a vibrational spectra or not, okay, or finding out a vibrational spectra or not for the molecules. Okay, so yes, we can easily find out vibrational spectra or frequency calculation, or you can say that IR spectra. Okay, not even UV visible, even IR spectra you can easily find out, and you can just uh, you can visualize that particular which bond is a stretch and which bond is asymmetric stretching or bending or this. So you can easily find out or you can easily um, uh, do a calculation with this ARCA software. Okay, so community and support, ORCA has an active user community and comprehensive documentation. The developer regulate update the software and provide support through a forum and mailing list. Free for academic use, ORCA is a free for academic user, making it accessible to researcher and student. Okay, so this is about ORCA software. Okay, and this is my mobile number and email ID. If you have any doubt in this software or this, you can reach me through this mobile number and email ID. And thank you for this session. And after this session, after I think 10 minutes break, we will continue to the uh, hands-on session. Uh, Sanjay sir?
Yes, sir. Yes, sir.
Yes. So I think after 10 minutes or 3 o'clock, we will start hands-on session.
Okay, no issue.
Okay.
Okay, thank you.